All right, we're starting day 2 of our crash course on polars and a little bit more on parametrics. So what we're going to do is kind of blend in the concept of polars with parametrics, because as you know, polars are written in terms of theta. So we have x equals something with theta and y equals something with theta. These are actually parametric equations right here. Um, but they're dealing in polars as well, because I don't know if you remember, but the basic polars are x equals r cosine theta and y equals r sine theta. That is how we transition from the polar coordinates to the rectangular coordinates. So there's a lot of similarities in here. And when we do a lot of polars, we're effectively using parametric skills. So let's start by calling these parametric equations x equals 2 cosine theta, y equals 3 sine theta. And we're going to graph them by hand, converting the equations to rectangular coordinates as well. So the reason why we do this is just to ground you in polars again. You know, we're not expecting you to remember all this, and you don't necessarily need to know how to graph polars from scratch. In fact, you don't need to know how to graph polars from scratch. But we want to walk you through this exercise so that you remember a little bit about polars. So if you recall from trig, and of course, many things that we've done this year, you know that cosine squared theta plus sine squared theta, sine squared theta equals 1. So since we have cosine equals 2 cosine theta equals x, we know that cosine theta equals x over 2. And since we know that y equals 3 sine theta, that means that sine theta equals y over 3. So we're going to use this trig identity and plug in our cosine theta and our sine theta. So cosine theta was x over 2, we have to square it. Sine theta was y over 3, we have to square it. And we end up with x squared over 4 plus y squared over 9 equals 1. And we're hoping that you recognize this as an ellipse. And if we were to graph this ellipse, we know we're centered at the origin because we don't have any subtraction from x or y. So here's our center. And underneath x squared is 4, so that means we move left 2 and right 2 on the x-axis. And the denominator of y squared is 9, so we move up 3 and down 3 on the y-axis, so we get an ellipse. If I could connect the dots, you'd really get an ellipse, but that's good enough. Okay, so that's just a little bit of a refresher. But what you're going to see here is that if we want you to find the slope of the curve at theta equals pi over 3, we're starting to think in angles instead of in x and y coordinates. Normally we would say find the slope where x equals 2 or x equals 20. But now we're giving you an angular value. If you recall, pi over 3 sits here in the first quadrant, maybe goes up like this. So the point of tangency might be around there. So we should get a negative slope at theta equals pi over 3. But how do we do that? Well, just like we did with parametrics, we take our parametric equations and we find dx d theta and dy d theta. No longer is our independent variable in terms of t, it is now theta. So dx d theta is going to be negative 2 sine theta, of course, because cosine differentiates to negative sine. And then dy d theta is going to be 3 cosine theta because sine differentiates to cosine. Then, just like with regular parametrics, to find the slope, you actually need dy dx. So you're going to take dy d theta, divide by dx d theta. So dy d theta was 3 cosine theta, dx d theta was negative 2 sine theta, and that is dy dx, or the slope of my ellipse at any point, at any theta value. Now we need to evaluate that such that theta equals pi over 3. So you do need to remember your unit circle values. We know that cosine of pi over 3 is 1/2. So you have 3 times 1/2. And we know that sine of pi over 3 is the square root of 3 over 2. So in our denominator, this 2 and this 2 can cancel. And I'm going to rationalize by multiplying by rad 3 over rad 3. So in my numerator, I'll have 3/2 rad 3. In my denominator, I am just going to have a negative 3. So nicely, the 3's will cancel, and my final answer will be the negative square root of 3 over 2. Thankfully, it's negative, just like I thought it would be looking at the graph of my ellipse. So continuing with this example and continuing work with parametrics, actually, we're no longer doing the basics. We're going to go to area now. And they want to know the whole area of this curve. Now, this is an ellipse. If I wanted to get area the traditional way, what I would probably do is just look at what's sitting here in the first quadrant. To do that, I would have to solve my equation in terms of x, and I would go with the positive square root because I'm not worried about the negative. And if I just worried about this quadrant, because of the properties of symmetry of the ellipse, I could just get this quadrant in a rectangular area fashion, meaning the traditional way you know of finding area, and I would multiply it by 4. But since we're dealing in parametrics, we have an easier way to do this. So if you recall from pretty much everything we've done, if you were looking for area, what you need is the height of the function times the width of each slice. So if we did that in terms of parametrics, we actually have separately the y value right here, and we found the dx value right here. So we can actually just write in here the y value was, I've already moved it up, my y value was 3 sine theta, and my dx value is 3 cosine theta. And of course I'll have a d theta here because I'm just looking for dx, so I had to multiply both sides by d theta. Now, that was crazy, wasn't it? That we just took, normally we've always said, okay, let's just integrate f of x dx to get our area. Well, f of x is just y. We have y separated, we have dx separated, so we can combine using parametrics to get this. We've now totally avoided having to solve for y equals in a crazy ellipse, which would have been difficult to do. Okay, so now the problem is, I don't know what my, let's see if I can get this to work here. I don't know what my limits of integration are. And I'm looking at this and I'm thinking, do I just go from 0 to 360 or excuse me, 0 to 2 pi? How do I do this? Well, remember when I talked about this section right here? That, if I had just integrated that rectangularly, I would have gone from 0 to 2. So what we're going to do is change those rectangular coordinates to be in terms of theta values. So to do that, I'm going to start with my 0 to 2, and these are x values, and if you recall, we had x equals 2 cosine theta. Let's just go up and confirm that we had that right. X equals 2 cosine theta. So if I plug 0 into x equals 2 cosine theta, plug in 0 for x, I get a 0 equals 2 cosine theta. And where is cosine theta equal to 0? Well, at pi over 2. Need to do the same thing for this x value. X equals 2 cosine theta, so 2 equals 2 cosine theta. Cosine theta equals 1. Where is cosine equal to 1? At theta equals 0. So what we just did was we transformed x values into theta values so that we can transition from our traditional area in terms of x to our new area in terms of theta. So our limits of integration are pi over 2 to 0. And if you recall, that only gets us this quadrant. So I still need to use symmetry to multiply by 4 to get the entire area enclosed within the curve. The good news is that you are going to do this now on your calculator. If you want to simplify it before putting it in, you have a 3 and a 3 times 4, so 36 out in front, pi over 2 to 0, sine times cosine d theta. Plug that all into your calculator, and it actually works out very nicely to be 6 pi.